Let's now calculate the self-inductance of a few cases. The first case will be a very long solenoid. So again, we have a current I coming into the solenoid, a current going out. It's wrapping around. And we have N, so that's the number of turns per unit length. And let's make this a radius r. So let's first focus on a single turn. So this is one turn. Now, in that turn, remember our solenoid has a magnetic field that's essentially uniform and zero on the outside for a very long solenoid. So in this one turn, we have a uniform B field. And we can calculate that B field by our typical Amperian loop calculation. B times L is mu naught Ni times L, or B is mu naught Ni. And so when we want to calculate the self-inductance, we're integrating. Now this is a little bit tricky. So let's write it first this way. It's the total flux through the solenoid divided by the current in the solenoid. And let's say, even though the solenoid is very long, let's say there's N turns. N is the number of turns. So the total flux is N times the flux through a single turn divided by the current. And that's why we're focusing on the flux in a single turn. Now, if this is a radius, r, this is an easy calculation. It's N times the B field in the solenoid times the area. And this is easy to remember if you're a basketball fan, NBA. And so we have N times mu naught little n I, the area pi r squared over I. And that's given by mu naught, capital N, the total number of turns, the number density of turns, times pi r squared. Now, suppose that our solenoid was a length, we'll just call that h. Then the little n is the total number of turns divided by h. And so what we get for the self-inductance of this solenoid is mu naught n squared pi r squared over h. And we'll make an approximation sign because we're assuming now it's a finite solenoid of length h. But that's a pretty good approximation. Now, what's really important to realize here is that L is proportional to n squared. Why is that true? Because the B field depends on the number of turns, the turn density, n divided by h. So the B field will depend on n. And the total flux in the solenoid that we need to calculate self-induction depends on the total number of turns itself, and that's the other factor of n. And that's why the self-inductance depends on n squared. And this is a typical calculation for self-induction.